Okay, so computing the average heat transfer coefficient from a correlation. So the first thing to note is that if I want to have the average heat transfer coefficient, h bar, that is going to be equal to the length-weighted integral, 1 over L, integral from 0 to L of the local coefficient, hx dx. Okay? So for flow over a flat plate, this there's a correlation that's Nusselt x is equal to 0.332 times Reynolds x to the 0.5 times Prandtl to the 1/3. So this is our correlation. Remember, Nusselt's related to the heat transfer coefficient as shown in the upper right. Reynolds for flow over a flat plate is computed as shown in the upper right as well. That's rho u infinity times x. X is our characteristic length there. So we have all the information we need in order to actually do this integral. So what you would basically do here is I'd say, all right, let's combine this where you say h bar is equal to k over L times the integral of 1 over x 0.332 re x to the 0.5 Prandtl to the 1/3. So 3/1/3 dx. I can bring a bunch of stuff out, and so this becomes h bar is equal to k over L 0.332. Prandtl is constant, right? Prandtl to the 1/3, that's constant. The parts of the Reynolds number that are constant would be rho u infinity, and mu. So those can come out. And then the stuff that's left inside the integral is 0 to L x to the minus 1/2 dx. Okay? So this is all just kind of subbing stuff in and bringing constants out. If we evaluate this, this integral becomes 2L to the 1/2. You can take my word for that. And so then what we end up with for our h bar is equal to 0.664 k Prandtl to the 1/3. And then we have rho u infinity over mu L to the 1/2. Okay? So it's really straightforward, right? All you need is the function in terms of x, integrate that function, and you get back your h bar. So maybe one of the reasons why I'm doing this or going to the trouble here is this is for, let's see, for laminar flow, right? Well, what happens if you have a transition from laminar to turbulent? Now you have, if you look back at this table, right, we have two different correlations for local heat transfer. You have a local heat transfer correlation for laminar flow and a local for turbulent flow. So how do you combine those two? Right, well, basically all you have to do is just do the combined integral of those two things. So it would be saying, okay, h bar from 0 to L, where that range now includes both a laminar region and a turbulent region. Right, that would just be, let's see, h bar is equal to, I'm going to integrate from 0 to x critical for the laminar part of it, x critical, 0 to x critical. For the hx laminar dx. And then add to that, right, so first you integrate up into the transition point, and then you integrate from the transition point to wherever you want to end up. So that just is plus 1 over, let's say, L is where we want to end up. So L minus x critical. We're only integrating the part that remains from x critical to L of hx turbulent dx. Right? So you would obviously take the functions for hx laminar, hx turbulent, plug those in, and then do the integral yourself. But this is just how you would sort of generally approach developing these. So when you look at the table actually includes these solutions already, like this one here. This is the combined integral of both of those things. Right? Questions? Yeah.
So the local is just for laminar flow, the average is both the laminar and turbulent?
So the question was, say it again.
From the table where it's the local value and the local just represents the laminar region of the represents.
In the table, the local represents the local value. If you were to just look at, say, laminar, so like here, this here would be the local value for, let's see, laminar flow, right? This down here would be the local value for turbulent flow. And then the integral here is the integral of the laminar only, the laminar function only, because obviously you wouldn't have had turbulent flow, right? So this is laminar only. Down here, this is going to include both laminar and turbulent. It's the integral over both of those regions.